All right, I am back again. Now it is Sunday, 2 days later, and we're still working on the ELO challenge. So I'll just recap what I tried last time and kind of do a synopsis of what I figured out. Um, for anyone just joining in, I basically started with a public kernel, just looking at what they did, kind of reviewing, seeing if there's anything obvious that I thought that I could improve. There wasn't really anything immediate, and so what I pulled out was this Bayesian optimization library. I didn't go into too much detail because I was trying to just wrap it up. Maybe I'll pull that up to show that off. So Bayesian optimization is this general idea that it's a complex statistical method, but my general overview of it is, at least the way that I use it, is that you can do random search and grid search, and that will just kind of go through a bunch of different hyperparameters, either randomly or in a systematic fashion. So if we look at this stuff, like, it would go through 30 and 45, and just, if you're doing grid search, you could say test every single one in between, or if you're doing random search, it'll just pull random points from all of these different hyperparameters or parameters of the light GBM that we're using. And this is okay, but the problem is if we have a lot of parameters, then that's very inefficient because we're trying every single variation of this and this and this and this and this, and then the search space becomes massive. And so what we can do is Bayesian optimization will look at the signal of all of those things, and we're doing optimization on our hyperparameters like we would do optimization using gradient descent or any other number of things. But Bayesian optimization is more well suited to something that might be slightly noisy like this, where there's some randomness involved. So if you're doing 0.1 and you change it to 0.2, it might not be enough in order to make a significant difference, and your 0.2 might end up decreasing results when in actuality you want to go to a 0.5 or something like that. It just happened that on that run it was not successful. So this Bayesian optimization library is really cool because basically you there's plenty of documentation, but it basically shows that it initializes using a bunch of random values, and then it kind of understands a little bit about the optimization space, and then eventually once it goes into optimization mode, once it's done all of these random points, then it will kind of key in on certain zones and try to figure out where exactly the function is minimized. And so if we look in here, that's basically what I did. I imported the Bayesian optimization library, and then you give it a function. And so that's what I did here. And in this function, what I did is I defined all of the parameters, and then I trained the model for 5 folds. I believe it was 5 folds, maybe 4. And then it measures its out of fold accuracy, and then I took the average across all of those, and then I return the value that we're looking to minimize. And so what you do is you give it this function, you give it all of the parameters and the ranges that you want it to try, and then you basically say maximize. Sorry if I said minimize a second ago. It only does maximization, and so that's why I had to do negative here, because if the value was like what a lot of people are getting is 3.7-ish. So if you're trying to, it only does maximization, so you're trying to get that number higher, and so if you make it negative, then you're just doing the same as minimization like we're trying to do on this target. And so that's your signal that comes back to the system, and then it uses that in order to determine which direction to go into. And you can define how many initialization points. So that's this stuff here where you see the dots popping up. It's figuring out what is the loss in these various different spots, and then how many times to actually optimize. And so this is all a decent idea, because in theory it should give us some hyperparameters that do better than just kind of the random that people had assigned prior. But we'll dig into this and we'll see why that was not the case in this specific scenario. So the Bayesian optimization library will print off all of the different features that it's trying to optimize for, and the time that it took to run that thing, and the value that it output. So it runs for all 5 folds, and then you can see those 5 folds ran for 2 minutes 28 seconds, and it got a value of negative 3.66826. And then these are all of the different parameters that it plugged in. And so we can go to the next one and we can see, oh, it actually did worse than the previous one. And so it will highlight whichever one is your current best, and it saves that. So like, I think I just scrolled past one. Yeah, so this it shows that it did better on that one, and it outputs all of those values. And so one of our problems, there were multiple problems with this trial, but the first one is it seems like it wasn't able to successfully converge. It gives this error, and in my experience, when it runs into that, it's basically saying that it can't solve this problem. The signal that it's getting is not cohesive. The gradient that it's looking at doesn't make sense, basically. And so if we look at the PowerShell that was running this, there was another problem. And so the other problem is that me naively defining all of these different parameters that I thought might be useful to optimize, it turns out that, let me find that window again. It turns out that some of them are overlapping, meaning that they can't be used at the same time. So like saying bagging fraction is set to this number, and subsample is going to be ignored, because bagging fraction can't be used at the same time as a subsample value. And I did that on a few different things, so there were some overlaps. And so I'm thinking that might be part of why this Bayesian optimization didn't work, because it had factors that were essentially being ignored. So we were adjusting values and nothing useful was happening. So that's one area that we can poke around in and see if maybe we have a solution for the output of this Bayesian optimization. You can output with dot results, and it will tell you the max, so what your best result was, what the parameters were at that result, and then it also tells you all. So it will list off every single result that you got, and then it will also list off every parameter variation that you tried, which is very nifty, because you can do some pretty efficient parameter search without needing to really do anything. You just throw compute at it. So that is all useful and good, but I don't think I want to start off doing Bayesian optimization and then just running it for however long. So I started a Trello board, and I'm going to start kind of journaling and putting all my ideas down so I can start outputting all of that. What was I going to do? Fix. Call that BO, just because it's funny. Remove overlapping parameters in Bayesian optimization. Alright. And then I did some reading. Let's look back at Kaggle. Just pulled up the live chat in case anyone comes in here. And so this is the kernel that we started off on. I'm going to sort by best score because I read one of the ones that was over here that was pretty interesting. So this one, the main takeaway I got from this, there's some good features, but I won't worry about that quite yet. The main takeaway that I want to pull from this is they used Stratified K-fold, and they just got way smoother validation results. And from what I was reading, one of the biggest problems is that there are about 2,000 outliers that just have huge value, and they totally throw off the model. They're saying, at least from what I was seeing from the discussions, it's taking up as much as basically half of your RMSE. So by stratifying it and making it so that they all end up kind of evenly throughout the folds, you can see that they're getting 3.65, 3.65, 3.65, 3.65, 3.64 in that one, but that's even across the board. And if you look at some of ours, we're getting 3.62, 3.78, 3.60. It's all across the board, 3.68. So adding that stratification will probably be very useful just in terms of consistency. So that's going to be probably the next thing that I work on, is Stratified K-fold. Hopefully I spelled that right. And so I am going to put that in the in progress, and we'll start working on ripping that out now. Shouldn't be too hard. Let's just copy that line. I'm going to do a side by side. Go way back up to the top, import Stratified K-fold. There we go. And we will do the folds up here. That should pretty much be it. I think that's all I really need. let me look, because he has a feature outliers that I don't have. So they do based on folds and whether they're an outlier or not. So let's build that feature first. Should just be that, I believe. Let's plug that in, see if it works. df train is not defined. Oh, we just named them train. Okay. Train, key error. Target. Did I split them into two separate? Not I, but whoever wrote this kernel, did someone split them into two different variables? Let's just look directly at train. So they split that out into a different... I don't know why I'm not... Let's go all the way back up to the top. Target, train.target. Okay. So we will just do... How will we do this? Oh, how about this? Target. That's probably not going to work, but I'll run it. Looks like it worked. Okay. So the issue here was that in this kernel, what the person did is they pulled target out of the data frame and then they just deleted it. So now target is just a separate variable and it doesn't exist in our training data frame. And so when we were going down here and trying to make an outliers column based on that target column, we couldn't do it because the information just wasn't there. And so now we should be able to say maybe I'll just copy and paste this to make sure I'm doing the right thing. Train, outliers, values, yeah. Dot values. Let's see if that works. Hopefully it does. One thing that's bothering me is it seems like these categorical features aren't necessarily working correctly. I'm going to have to look into that. Let's see how you're supposed to do categorical. No, it might be something actually changed. Let's see how he did categoricals because his isn't throwing that warning. They just had it commented out. Interesting. So we got our first result and it's 3.666. And so clearly those features seem to have done something successful. I am thinking, because of what I read from the forums, I'm wondering if it might just be better to do some sort of outlier detection thing rather than even try to make these predictions organically. So maybe do some sort of two-tiered system where we're just trying to pull the outliers. After this finishes running, let's try looking at, we'll do the feature importance again, but we will also look at the outliers. So we'll look at train outliers equals true. I don't remember if I need to do equals or not. We'll find out. So we'll potentially integrate the features from top kernels. This should be done pretty soon. So that got 3.66809. Huh, that is a sizable difference. Let's see what they... Well, that is just not useful. Let's make this full screen and see if that helps at all. There we go. Auth purchase date max. So I'm assuming that's something to do with the oldest authorization date and the oldest purchase, or the newest. I'm not sure, but and if we look at the other one, hist month diff mean. What is that? Hist month. It might never be explicitly defined it because I think you just did some sort of looping function. Hist month diff mean. Let's figure out where that came from, because that obviously seems like a useful feature. So it happens somewhere in this column because he's iterating through month, hour, week, year, blah, 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 blah. What is month diff? Month diff is the mean month diff is that would be sort of like our elapsed time, I believe, plus the month lag. I don't think we have anything that complex in ours, but I think this captures something relatively similar. We'll have to do a side-by-side at some point. So let's look at the outliers. It looks as though they're primarily recent. We should compare histograms of these features for outliers or not. df.hist. Let's try that. That's gonna just totally blow up because I didn't pick which feature I want. Let's start with the, what was that called? I know I can probably just do it this way. Okay. I'm kind of wondering if I want to... Interesting. So there's clearly a slightly different trend there. Even just purely based on dates, you can see that 2017 had way more here than it did in 2018. But at the same time, this is such a small count. But it is a difference of probably over, it's over 200, probably 250-ish. Well, I guess it is time to just print everything. For call in columns equals for call in train.columns. We'll print call so we know what we're doing, and then we'll plug in call to have all of those updated. It's gonna throw an error, almost guaranteed, but we'll see what happens. Yeah. I will be lazy and just put this in a try except pass so that I don't have to do anything more intelligent than that. I forgot there's so many features. This is going to be a problem. Hmm. I don't know how that would have happened even inside of a try except. Let's just do the first 10. Wow. Thank you. Oh, I'm stupid. Through the 10th instead of just the 10th. There we go. Maybe we can get away with the first 5? No. I guess I will just do it one by one because I don't want to mess with that too much. I think we can clearly see that there is, some people were saying that maybe this is just a data entry error. I'm not super convinced that's the case. I think that there might be something going on that we can suss out and find a pattern for and eventually predict. I'm going to skip one because I know that's card ID. It's only plotting one of them. That might be part of the problem. I don't think it's really worth delving into that deeply. The dates alone kind of showed me that there is some measurable difference between the two. Maybe it's just noise, but I think that what I am going to do is I will make the outlier the actual prediction. I'll make that the target and we'll see how we can do. If we can't predict beyond a certain level of accuracy, then it's not worth it. But so that would be train outlier. That should be it, I think. It's probably not going to work because it's true false, but we'll see. Key error, outlier. I'm pretty, outliers. Okay. Let's see. I think for this we might actually want F1 score rather than, can light GBM do F1 score? What's interesting is we're making these predictions and it's comparing the out of fold to the target, which is just zeros and ones, and we're able to get 3.87804, which is reasonably good considering we're not even trying to predict the correct thing. So I'm thinking it might be time to look at the light GBM documentation for binary stuff, because root mean squared error is just not the way to go on that. I saw it cross entropy probably. Let's see what else they have though. Default is regression. I don't need regression anymore. Binary log loss, we could do that. See cross entropy. Let's just do X entropy and see what it does. Where is that defined though? I feel like there might have been some metrics and stuff in there we didn't want. Yeah. Let's do classification. See how that does. I guess we'll go with binary rather than classification. Hopefully that works. I'm hoping it just doesn't learn to always guess not an outlier though. That's the key. That's why we need F1 score. So I would say stratified K-fold done, features not done. Now we're trying to do, what are we trying to do? Totally blanking. Oh, predict outliers. Predict outliers. Hmm. The results of this don't entirely matter, because I'm assuming cross entropy isn't really going to capture what we're even trying to do, because the problem is if you the outliers are extremely large values, so if we have any false positives or false negatives, we're going to be significantly hurting ourselves. So we probably want um, we probably want f1 square, which can capture that metric rather than just using accuracy or something like that. Let's pull this so I can look at both of them. So train takes in params, train data, number of rounds, validation set, all of this stuff, and it's going to need f eval and eval results. Hopefully that'll work, and I'll break this across a few more lines because this is getting long. And we will see if that runs. Invalid syntax. No. Oh, comma. There we go. Hopefully this works. F1 of 0. Wow. I'm going to have to turn down the early stopping. Maybe I'll just comment it out for now and just see if it can get anything in many, many rounds. Hopefully eventually the training F1 will even move. But there is also the potential that something is wrong with that metric. But we'll see if just totally... There we go. F1 is finally moving. Alright, I am going to go to the bathroom, but I'll let this keep running. And when I come back, we'll see exactly how it did. Alright, let's see how this did. It looks like it's possible to get your validation F1 up, so that is good news. And it's even possible that we just threshold this in some way, and then we can I don't think this will necessarily be useful. Maybe there is some way we can utilize this. I'm not exactly sure how. But if we could accurately predict this, that would be pretty solid. The nice thing about this is it's based on a threshold. So right now we're using, I looked in the function and it was using NP round, which means just round up or round down for the predictions. But in theory, what we could do is we could threshold it at like 0.99. If it's below 0.99, just default it to be a legitimate sample. If it's above 1, mark it as an outlier, or above 0.99, then mark it as an outlier, and then we could get a few more of those correct without showing a bunch of false positives. Hopefully there's some way that we could accurately discover that. The problem is this value is very low, so we'll have to see if that ever improves. Is that an up or a down? That's an up. So I guess while that is running, let's just look back on Kaggle and do some reading. Maybe let's do an EDA so we can actually learn something instead of just looking at some messy optimized code. I think potentially one step, let's mark this down, is add XGBoost, add cat boost. Never actually used cat boost, but we'll see. And I still think there is some hope for user embeddings and merchant embeddings. I have never done that though, so I'll need to do some research on that. That's not good. That started going down. The interesting thing is that no, it does look like this is kind of tailing out. We'll let that keep running. We'll just let it do the full 1,000 for whatever reason, and then we will take that best output and we'll see if we can threshold it in some way. For those of you who are not familiar, this is likely, hopefully there's a good image of this. This is likely something useful that we might use, receiver operator characteristic, which is basically a graph showing false positives versus true positives, I believe it is. I'd have to double check on that, but basically this is, as you change that threshold, how does your true positives versus false positives change? Or no, it's your sensitivity versus your specificity. And so basically this is saying at a threshold of 0 you are predicting every single one is going to be above that threshold, and at 1 every single one is going to be below that threshold, and as you change that you are getting a slightly different result, and you're going for the point on this that is farthest away from this line, basically. And so that is typically over near here, but you can tune it based off of your tolerance for false positives, false negatives, whatever, based off of what the cost is. And so for our scenario, we probably, ideally, we could just pop off a few false positives, or no, we could pop off a few true positives and then have those filtered out so that they don't affect our model, and we can accurately predict them as something that is out of a reasonable range. And so the way that we found these outliers was pretty simple. I don't know if I covered that at all. So the outliers, basically, they made a column that's outliers filled with zeros, and then anything that is below -30 they marked as an outlier, because almost everything falls between -1 and 1. So anything that was -30 was just way out of bounds, and so that's supposedly these 2,207 are what's causing about half of our loss. If we drop the outliers, then we're able to very accurately predict. Hopefully that finishes up soon, but I guess we'll visit back in onto this EDA. So this is showing that there are, I think we're likely missing some of these. Actually, no. I guess that there's this bundle that's disconnected all the way at -30 that is likely the issues. I kind of wonder if there is some way that we can transform this graph so it was more condensed and our model is able to reach it more efficiently. I don't know of how to do that necessarily, but typically with something like this where there's just a bunch of outliers, let's say it's a curve where we're looking at a histogram and it looks something like a long tail, then you can do a long tail on the right. Then you can do the logarithm of that and it will condense it and it will make it look more like a normal distribution. And so here we see that we've got our normal distribution, but we have a very big negative tail. So this is what we plotted out, but he did a much nicer job, and he got all of the timestamps on there. So this is the train versus the test. Looks roughly the same. Feature 1, feature 2, feature 3. They all have roughly similar distributions centered around 0. Number of historical transactions. That's interesting. It's kind of bizarre that someone with so many historical transactions would not have a significantly better. This is kind of an unclear graph because we have a few outliers that are really just skewing things. So I am going to focus in on that portion. And it seems like the general trend is upwards, where the more transactions they have, the better. But it also seems that as more transactions occur, they basically just are perfectly centered. I'm excited for this thing to finish and see if there's anything we can do with filtering off some. Because if we can even filter off 5%, that would be huge, because those are contributing so much to our loss. And then I guess we could, let's plot feature importance too once that's done, so we can look at what might have caused. Oh my god, this is going for all the folds. That is not gonna work out. So that made, dang it. So that made predictions though. It should have. Let's see what predictions looks like. I wonder if there is a way I can do that without doing. I think I might have to just go old school with the train test split. But then the outliers aren't going to be mixed evenly, which is a problem. Huh. I'm thinking I can likely do something with what we already trained. I'm thinking these shuffles should be the same every time, so I'm thinking I can just do if I do folds split zero, that should output the indexes, I believe. Generator object is not subscriptable. I just need some way in order to pull out the first one of those, basically, because I need this validation index. There we go. And I only really need the first one. I'll just copy this line, and if the enumerate is not above something, I'll just continue. Let's say less than 1. If fold is less than 1, oh, if it's greater than 1, so it's starting at 0, then it goes to 1. If it's greater than 0, let's try that, that should be it. That's not what I want. That'll do it. That's not the most elegant way to do it, but whatever. Okay, so I have that. Now, take this, and then I can do OOF, val IDX, 1. Now I've got all of those ones that I just trained a classifier on. Maybe I can plot the feature importance. I'm not sure if that's going to work. Where did I even hide that away to? Feature importance. Oh, there we go. Might not work, might work. I don't know if that's fully updated. Whatever, we made a mess of that. So those are our predictions, and our labels are that. And we are looking at the F1 score. Where did that go? There we go, F1 score. We probably want precision and recall more than anything, actually. All right, nope. With number, inconsistent number of samples. Are you kidding me? Oh, okay. We can do that. Oh no. Continuous and binary targets. So let's do np.round. There we go. So this is the value we were expecting. That's good. Let's pull out precision and recall though. Scikit learn precision score, that's what it is. Maybe recall score? Yep, there we go. So let's copy this a few times and do precision recall. Print. See how that does? We get a recall of 0.5, which doesn't seem great. Let's read through these. So precision is ratio of true positives over true positives plus false positives. So that's more or less how many positives it got correct over. It's basically just how many positives it got correct. What ratios of positives it got correct. So it got 0.5, which is actually pretty good. Let's see if I'm thinking that we can do some threshold in range 0, 1, 0.01. And so my goal here, I don't know what I'm doing with my spacing, is move the threshold through that range and see if there's something where I get a good good value. So let's do greater than threshold. Let's see if that works. No. OF. Let's look up threshold NumPy array. That looks fairly simple. Does it just need parentheses? Let's just take this specific statement out and see if we can get that to work first. So let's break this down. Threshold is not defined. Let's just put that at 0.5. So that works. Now we need to do OOF. Set num, there we go. That should be it. This should do it. Let's check it out. So 0 if for a in, let's do this. Zero if a is greater than the threshold. I'm going to switch that to 1. Else, I don't remember where this else statement goes, but I'll put it there and see what happens. That looks correct. Let's see if there's any. Okay, so there is in fact a 1 in there, maybe a few, but let's just plug these. I just need to calculate this once. Thresholded equals that. Threshold. I don't need any of this garbage anymore. OF thresholded that. I think that's enough. Let's see what that does. Float object cannot be interpreted as an integer. What does that mean? I've definitely done this before, because it's just, let's look at the range function in Python. You know what? It might be numpy.arange. There we go. And I am going to need to write these down in some way and then plot them. So let's do F1 score equals list. Let's do these all at once. Precision. F1 precision recall. One dot append. I can do that, but I also would like, how about I define this up here so I have some way to also know the values where the maxes and the mins occurred. So let's do thresh, oh crap. Thresh range equals mp dot a range. Let's do that, and then let's do plot dot. I always forget how to do this stuff. Matplotlib line plot. It should be the simplest thing. It's plot dot something. Plot dot plot, and then just plug the x and the y in. So x will be thresh range, and we'll do f1. We'll do these all as separate plots. Run that. Perfect. That is what I wanted. How is there syntax error? Is this missing a closing one? Yeah. Nope. Now this, hopefully that works. So the F1 can be brought up 2.2, which is actually pretty impressive considering how imbalanced this is. Precision, recall. So there is a region where recall can be 100%. I need to brush up on what these exactly mean. Precision recall curve, it might do that for you. I already have precision recall. These are interesting. I'll skip over AUC for now. Let's look at the precision recall. So thinking about this, which one do we care about most? The precision is intuitively the ability of the classifier not to label as positive a sample that is negative. So, number of true positives and false positives. Precision is intuitively the ability of the classifier not to label as positive a sample that is negative. Hmm. These are very interesting shapes. What I should do is look at the train val idx1 let's look at this and see exactly how many are even. Dot block. I think that's what I need to do. Dot ilock. No. What did we do up here? That is what I need. Outliers. Oh my god, every time. Let's do describe. I don't understand what that plot is trying to show me. Let's just look back at this and do a count of some sort. Value counts. So we got 442 in our validation set. I'm trying to think what we can do with that. If we set a very high threshold, I might have done these in the incorrect order. Let's reverse that, because I think I did that wrong. Those curves don't make sense to me. That makes more sense now. I feel like something is going wrong though, because those totally changed. 0 if a maybe we pull out the confusion matrix, because I think that'll make more sense. Let's just look at the one in here. Confusion matrix. Confusion matrix. I don't know if I really want that many of them. Let's just pick a value. let's pick, I don't know, let's just do 0.5 and see where that gets us. Fusion matrix, not important. So I need to look at what this is. This is true positives. So the output is returns we do dot ravel on that. And then that gives us true positives, false positives, blah, 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 blah. True negatives. I don't know why true negatives is first. False positives. So our focus is capturing true positives without getting any false positives. So our goal is true positives over false positives, basically. We want our false positives to be basically 0 and our true positives to be very high. So the second and the fourth value. That is pretty good, actually. So I'm assuming this is getting 439 out of 30, correct? So let's say we could So we've got these predictions. What we need are regular predictions, the outlier predictions. Let's do this just for one fold. But let's also make sure that we have what we need. We already have the out of fold thresholded, which should be all we need, I think. Let's just save that away. For now, to make sure we don't lose that. I don't know if this is making sense what I'm trying to do, but I'll just kind of talk through it to make sure that it is. So what I'm trying to do is I want to output regular predictions, the ones that we were getting 3.65-ish on 6, and then train those normally. I'll just do it for one fold. And then I will see how that performs, and then compare that to what it would perform like if we dropped those outliers. So if we just guessed -30 for those outliers, because it looks like I'm actually able to get those relatively accurately if I'm doing that correctly. I'm not sure if I am. Because it says 39939 seems pretty good if I'm understanding that. Unless this is false negatives. I think I have this the wrong direction. I think I was right the first time. Let's redo this. So this is, I need to copy this over. So true negatives, false positives. That's not great. False negatives, true positives. Let's see if there is anything with this threshold we can do that might alleviate that. Let's just do a loose search for now. So 439 and 3. False positives, true positives. What if we just put this value really low and we just filter off like a few of them? So that's your false positives, true positives, and then your true negatives, false negatives. I keep getting confused. I'm kind of getting burnt out on this. I'm thinking I'll probably take a lunch break and then maybe come back to this. So I will put a note to myself using confusion matrix in order to try to filter out true positives without many false positives. Alright, and I think that will be it for now. I think I'm just gonna go get lunch and then come back though. So hopefully I'll be on in a little bit.